Hello world, hello Philippines. I will be able to discuss regarding the Vanthoff factor. Okay, the Vanthoff factor is all about the total number of ions, right? During the dissociation of the electrolytes. For example, um, calcium hydroxide, sodium chloride, like that. So mainly those are salts. Okay, so this sodium hydroxide, calcium chloride, okay, this is always under the product of hydrolysis reaction. Okay, it is a hydrolysis reaction. Okay, so meaning the reverse of neutralization reaction. Okay, so we should always add the salt with water. You know, water, and then if we add with water, that is a KU solution. Okay, so for example, we take the two electrolytes, calcium hydroxide or sodium chloride, for example. Okay, so each of them will be added to water. Okay, so sodium chloride plus water. Okay, so that is a KU solution already. Okay, and sodium hydroxide plus water, so that is a KU solution already. So there is water. Okay, so in this manner there is a degree of dissociation. Okay, if we add water, so we can say uh, before dissociation and after dissociation, something like that. Okay, so in this manner we have the dissociation factor, of course, right? So our dissociation factor will be the dissociation of the gases or aqueous solutions. It depends on the context, but here we use electrolytes. Okay, the dissociation of the species. Okay, after dissociation, and the dissociation of the species before dissociation. Since this is dissociation factor, then you have the denominator and the numerator. So our denominator will be the dissociation of the species after dissociation over the dissociation of the species, okay, before dissociation. Of course, before dissociation, our time at that point is uh, 0, right? And after dissociation, our time will be, for example, 2 seconds, 3 seconds, 4 seconds, like that. Or you can simply state that as t is equals to t, wherein t is considering what time for that. Okay? Since I am sleeping, I cannot illustrate it with through discussion by writing. So it is better to understand by writing, right? Okay. Now, you remember the colligative properties in the computation of the boiling point elevation or the freezing point elevation. Okay, so the formula have I, right? I is the Vanthoff factor. So the Vanthoff factor is equal to the dissociation factor also. Okay, and now the total number of ions will be equal to the Vanthoff factor. Okay, immediately. Why? Because in that manner, we are assuming that there is a 100% degree of dissociation of the species. Okay? So 100% degree dissociation of the species, meaning complete dissociation. Okay? So our dissociation factor will be basing on that, and our Vanthoff factor will be basing on that. Okay? Like that. So we can say that the total number of ions after dissociation, okay, is equal to the Vanthoff factor and dissociation factor. Why? Because we assume that there is a degree of dissociation which equals to 100%. Okay, like that. So it's better to show to you the formula so that we can understand also. Okay. Wait. Wait for that. My gosh. Okay. I'll show you like this. Uh, I, I told you a while ago that that is a hydrolysis reaction, right? The reaction of salt and water to produce acid and a base, okay? So let's say hydrolysis reaction, okay? Hydrolysis okay. Remember our topic is um, Vanthoff factor and dissociation factor. Okay, that is very necessary in the computation of the colligative properties. Okay, for example, the freezing point depression, the boiling point elevation, vapor pressure lowering, something like that, and the osmotic pressure. So the three of which incorporated the value of I. If there is an examination that will ask what is the another term or what the another name of Vanthoff factor, that is automatically the dissociation factor. Okay, like that. Okay. So we have the hydrolysis reaction. Okay. So that is, for example, we take the reaction of sodium chloride plus water, okay, because this hydrolysis added with water, or a reaction with the addition of water to the salt, okay, like this. Let's say sodium chloride or the table salt plus water. So this example of a chemical reaction, okay, is not synthesis, it's not decomposition, okay, it's not also single replacement and single displacement. Okay, we will review the type of chemical reactions, right? And it's not also combustion, of course. This is double replacement and double displacement in the presence of, so our product will automatically be weak acid and weak base. Okay. Oh no, not weak base and weak base. It is naturally strong acid and strong base. Sorry, because of the chloride and the hydroxide. Okay. So it should be HCl plus, okay, sodium hydroxide. So strong acid plus strong base. This one. This is hydrolysis reaction producing strong base and strong acid. Okay, so after that we balance the chemical reaction. I think this is automatically balanced. Check. Automatically balanced or not? It's not. We need to balance this. Okay. Okay. Sodium 1, sodium 1, chlorine 1, chlorine 1, hydrogen 2, and hydrogen 2, oxygen 1, and oxygen 1. So we balance the chemical reaction. Actually, this is balanced. Sorry for that. Okay, I thought it was not balanced. Okay, but in this case, in hydrolysis reaction, we have a perfect chemical reaction. Okay, so we have sodium chloride, table salt plus water is equals to hydrochloric acid, strong acid plus sodium hydroxide, which is a weak base. Now our topic is Vanthoff factor and dissociation factor. Since we know this is represented a small letter I, okay, small letter I. So this is the dissociation factor and the Vanthoff factor is just equal, okay, like that, and this is represented small letter I, okay. In this equation, okay, the HCl is our concern, okay, because our concern is the electrolyte, which is coming from the salt sodium chloride. So we are concerned for this in the colligative properties, because in the colligative properties we are dependent on the number of ions or molecules, okay, like that, but not on the nature and the identity of the species, okay, like that. So we are interested in the sodium chloride added with water, okay. We are interested to the sodium chloride added with water. So we need to have dissociation factor for that, or the Vanthoff factor for that. Okay? But before that, we have the dissociation factor and the Vanthoff factor. Okay? So we have two formulas for this. Okay? We have I is equals to 1 plus alpha V minus 1, wherein V is equal to total number of ions. So this is our formula for so we have this equation for our dissociation factor, okay. So 1 plus alpha times V minus 1. Okay. So what is the value, what is the V in this equation? The V is the total number of ions, and the alpha is the degree of dissociation. Okay, degree of dissociation. So alpha is the degree of dissociation. So we are dissociating here the salts in water, okay, like that. Okay, so for example, if we try to dissociate this sodium chloride in this, okay, it's coming from here, right? Okay, it would be dissociation. So sodium chloride is equal to sodium positive 1 plus chloride negative 1. This one. So this is our dissociation. Sodium chloride is equal to sodium positive plus chloride. Okay? Like the positive plus negative is equal to 0. So this is completely stable. Okay, like that. Okay, in the dissociation, before dissociation, at time is equal to 0. Okay, our value of sodium chloride will be, say, 1. And then the value of our sodium positive will be 0. 0. Like this. After dissociation, it will now become 0. Okay? And then our sodium chloride is initially at 1. Okay? Before dissociation, before dissociation, at time is equal to 0. Okay, our sodium is 0, our chloride is 0, and our sodium chloride is 1. Dissociation, okay? And then at time is equals to 0. Okay, and time equal to, let's say, 2 seconds, 3 seconds, 7 seconds, 8 seconds, like that. So t is equals to t. So at t is equals to 0, okay, our dissociation will be represented in this manner. Let's say 1, okay, mole of sodium chloride, example only, and then you have the 0 mole of sodium and 0 mole of chloride, something like that, okay? And then at time is equals to t, meaning 10 seconds, 20 seconds, 30 seconds. So we have 1 minus, like this. So we let the degree of dissociation, okay, we let the degree of this dissociation as alpha. It's shown here, right? Alpha. So the degree of dissociation at time t. Okay, we are now having 1 minus alpha, okay, during dissociation, or after dissociation, sorry. And then alpha, and then alpha, okay? So meaning, this one here, 1, 0, 0 is before dissociation, and this 1 minus alpha, alpha is after dissociation, and alpha is the degree of dissociation. Okay, like that. And now we will solve now the value of I is equals to Vanthoff factor. Okay. Now, in a colligative properties, solving in the osmotic pressure, boiling point elevation, and freezing point depression, we really have a perfect degree of dissociation, okay, of alpha, which is equal to 100%. So that means 1. Our alpha is automatically 1. Okay, like that. So 100% degree of dissociation. Okay, 100%. So 100% degree of dissociation, alpha. So alpha is equal to 1. Okay. Therefore, alpha is equals to 1. Okay, because in this colligative properties, okay, we are considering a perfect dissociation of salt or electrolyte, something like that. Okay, and we are having A is equals to 1. So this should think our degree of dissociation is equal to 1 to the equation here, which is I, or Vanthoff factor, or dissociation factor, is equal to 1 plus alpha times V minus 1. Okay, the sodium chloride. Okay, we have now 1 plus I is equals to 1 plus A V minus 1 in this equation. So we need to compute first the total number of ions V. Okay, so total number of ions V is equals 2. Total number of ions 2 for sodium chloride. Why? Okay. Because sodium chloride, sodium positive plus chloride negative. So we have here 1 is equals to 2. So our V is equals to total number of ions is equals to 1 from sodium and 1 from chlorine. Okay, so our total number of ions is 2. Okay, now substitute I, Vanthoff factor, or dissociation factor, is equal to 1 plus 1 times 2 minus 1. I is equals to 1 plus 1. So our dissociation factor, or Vanthoff factor, is equal to 2. Okay, if you notice, our dissociation factor, or Vanthoff factor, I, is simply equal to the total number of ions in the dissociation of sodium chloride. So that's why in molality, or in the colligative properties, boiling point depression and boiling point elevation and freezing point depression formula, our I, we can say our Vanthoff factor I, or dissociation factor I, is automatically equal to the total number of ions during dissociation, because we assume that there is a perfect dissociation process, that there is a 100% degree of dissociation, which is equal to 100%. Okay, 100% this degree of dissociation, which is equal to 1. Okay, like that. That's why we automatically do in this manner in getting the I. Okay, for example, in calcium, let's say calcium carbonate, for example. Okay. Calcium carbonate, or the limestone example. Getting I. So, example, calcium carbonate. So, like this. For the calcium carbonate. Okay. For the calcium carbonate, we need to compute the dissociation factor I or the Vanthoff factor I. Okay, simply equal to the number of ions dissociation. Okay, during dissociation, because we assume a 100% degree of dissociation or equal to 1. Our alpha is equal to 1. Okay, like that. So we can say the total number of ions during dissociation, okay, is equal to the Vanthoff factor or dissociation factor, because we are assuming a 100% degree of dissociation, and then which is equal to 1. Okay, like that. So calcium carbonate will dissociate into calcium positive 2, right? Okay, and then carbonate, which is negative 2. Okay, like that. Okay, calcium carbonate, which is one form of stone or rock limestone, okay, dissociates into calcium positive 2 charge plus carbonate negative 2 charge. The two charges will be neutralized if we add these two charges equal to 0. Okay, so no need to add one carbonate here to balance with calcium, and no need to add one carbonate one calcium also to balance with carbonate. So it's already stable, something like that. Okay, so how can we compute the total number of ions? So it's just like this. 1 plus 1. 1 plus 1. Okay, just refer to the coefficient. Okay, because the carbonate is a polyatomic ion. This 3 is not the is not the subscript of this compound. This is already a natural polyatomic ion formula. So it's still 1, the subscript of the entire carbonate polyatomic ion. Okay, so 1 here, carbonate beside here, and 1 calcium. So this is ion. So total number of ions is equal to 2. Since we know dissociation factor is equal to the Vanthoff factor, so total number of ions is equals to 2. So V is equals to 2, I is equal to 2. Okay, so our dissociation factor is equal to 2, because it's equal to the total number of ions if we have the 100% degree dissociation. Okay, 1 almost all the time in the colligative property. Okay, like that. So let's prove it. So I is equals to 1 plus alpha V minus 1. So 1 plus 1 plus 2 minus 1, 1 plus 1 times 1, 1 plus 1 is equals to 2. I see, by using the formula, okay, dissociation factor or Vanthoff factor I is equals to 1 plus alpha times the total number of ions minus 1. So we have total number of ions of 2. Okay, substitute that in this equation, and the alpha also, which is 1, because 100% degree of dissociation. So our Vanthoff factor or dissociation factor I will be equal automatically to the total number of ions. Okay, no need to show this every time, because we have now the theory that the total number of ions during dissociation, okay, of an electrolyte or any source of whatever, okay, dissociation is really assuming a 100% degree of dissociation. Okay, you just total the number of ions. Okay, like that. So this I will be now substituted to the formula and equation of that boiling point elevation, freezing point depression, osmotic pressure for the colligative properties. See more on the ions. Okay, because our definition of colligative properties is dependent to the number of ions or molecules, like, and not to the nature and identity of the solutes or species. Okay, like this. Going back to our hydrolysis reaction here, right? Sodium chloride plus water, HCl plus, what's this one? Sodium hydroxide. Okay, we are not concerned for the uh, hydrochloric acid. Okay, we are concerned in the sodium chloride with water because we are adding the sodium chloride with water in aqueous solution. So this will be dissociated. Okay, like that. Okay, the hydroxides will be dissociated. Hydroxides here and HCl here. Okay, we are really focusing on the dissociation of sodium chloride in aqueous solution water, not for here, because here is morely referring to the identity or the nature of the substances. Okay, if we account these two products here, but since we are only concerned with the ions and molecules of the solutes, so we have sodium chloride. We focus on the sodium chloride dissociation, which is sodium plus chloride. Okay, here. Okay, now we have the formula for dissociation factor or Vanthoff factor. Okay, 1 plus alpha or degree of dissociation plus V minus 1. Okay, we can have also another formula for I. Okay, which is so a dissociation factor or Vanthoff factor. It's just the same, huh? So we have the dissociation species after or during the dissociation, which is like this. Okay, dissociation species. After dissociation and dissociation species before dissociation. Meaning here, at time is equals to 0, and here at time is equals to t. Here. So we have now our Vanthoff factor, or our dissociation factor is equal to the dissociation species, okay, after dissociation over the dissociation spaces before dissociation. So before dissociation, we have time is equal to 0. We have no time yet. Okay, and then after dissociation, we have already a time, or during dissociation, we have already time, which is t is equal to t. Okay, like that. Now, since we have this example here, sodium chloride plus sodium positive plus chloride negative. So, what are the dissociation species before dissociation? Denominator. So 1 plus 0 plus 0. And then we have the dissociation species, okay, during the dissociation or after dissociation. We have 1 minus alpha, alpha, alpha. So 1 minus alpha plus, what's that? alpha plus alpha. This is for chloride dissociation. Okay, dissociation factor or Vanthoff factor. Okay, dissociation species. Okay, before dissociation, numerator. Sorry. Yeah, denominator. Sorry, denominator, the lower part. The numerator is the dissociation during or after the dissociation. The dissociation species or the particles, right? Okay, during dissociation or after dissociation at time is equal to t. So we add this one, we divide this one, numerator divided by the denominator. So we need to cancel out the a here. So 1 plus a over 1. So since our degree of dissociation is 100%, so our alpha is 1. Okay, so automatically our dissociation factor is equal to 2, or Vanthoff factor is equal to 2, which is equal to the total number of ions during the dissociation of sodium chloride. Okay, this is how to get the I in the computations of colligative properties for the freezing point depression, boiling point elevation, and the osmotic pressure, something like that. Okay. Like that. So now if the problem will say that if, for example, in an aqueous solution of calcium chloride, so if what is the let's say the number of moles of calcium and chlorine, okay, after dissociation, like this. Okay, if we have percent degree dissociation of 80%, okay, you can compute like that. So automatically 80% degree of dissociation is equal to 0.8 or 0.80, something like that. And the same manner like this. Okay, so for example like this, calcium chloride. Okay, so this will be also helpful in the dissociation of gases also, and also in the solubility product constant or the TSP. Okay, same story like that during dissociation, same principle. Okay, so for example calcium chloride. Okay, we have 80% dissociation of calcium chloride. What is the dissociation factor? You can now compute for that. What is the Vanthoff factor by using the two formulas? Okay, I presented a while ago. Okay, so calcium chloride. Okay, calcium chloride dissociation is calcium positive 2 plus chloride. Okay. Actually, this is the dissociation of calcium chloride. Calcium positive 2 plus chloride. Now the calcium has positive 2 charge and the chlorine has only negative 1 charge. So to positive 2 and negative 1 is not balanced. So we need to add one more chlorine in this side. Okay, like that. So plus chlorine. So we have now 2 chloride. Okay, so we have now 2 chloride. It balance here in the positive 2. So chloride plus chloride is equal to 2 chlorides. So we have now, okay, so 2 plus like this. Calcium chloride plus calcium positive 2 plus chloride negative 1. And we have to add one more chloride to balance the positive 2 charge of calcium. Okay, so chloride plus chloride equals to 2 chlorides. Okay, so our dissociation will now take place as, okay, calcium positive 2 plus 2 chloride. So our dissociation species of calcium chloride will be now like this: calcium positive 2 plus twice of the chloride negative. Okay, so what is our total number of ions? V. Okay, is equals to 1 plus 2. 1 plus 2 is equals to 3. Okay. One for calcium and 2 for chloride. That is the total number of ions. 1 for calcium plus 2 for chlorides. Calcium and chloride. So 1 plus 2 is equals to 3. That is our total number of ions. Okay. Now we will compute to the dissociation factor, and the Vanthoff factor will be also equal to 3. Okay. 1 plus alpha b minus 1. This, our Vanthoff factor, dissociation factor, will be always like this. So there is a perfect degree of dissociation, which is 100%. Okay, so A is equal to 1, like this. 1 plus 1 minus 3 minus 1, 1 plus 1 times 2, then 1 plus 2, I is equals to 3. So our dissociation factor or Vanthoff factor is equals to 3, the same as our total number of ions V. So you will no longer compute the dissociation factor or Vanthoff factor in this manner. We can automatically go to the total number of ions of V to make it easier, because it will take time a lot. Okay? Because usually this I is not given in the computation of the colligative properties. It's always computed. If we have the knowledge that this total number of ions is the V, or the, okay, and then automatically we don't have to compute the dissociation factor, the Vanthoff factor. We always consider this analysis always, because we are assuming that there's a percent degree of dissociation, which is 100%. Okay. Now, since we have this dissociation for calcium chloride, it will now be like this. So calcium chloride so at times the dissociation of the species, okay, before dissociation, the dissociation species before this time is equal to 0 will be equal to, starting from 1, because this is 1 because the coefficient, so is 1, starting from 1, okay, and then starting from 0. So always 0 if separate electrolytes. Okay, it's calcium positive 2 plus 2 chlorides, because these are ions. We will start 0 automatically for this. Okay, for the electrolytes with charges, always 0 at the before dissociation. At time 0 before dissociation, this electrolytes calcium positive 2 and chlorides negative 1 should always start initially at 0, 0 before the dissociation. Okay, except for calcium chloride, it starts originally as 1. Okay. And then at time is equals to t, or at time is equals to t, meaning to say at any time. That's why it's gonna be like this. It's gonna be 1 minus the degree of dissociation alpha, and this will become now alpha, and then alpha like this. Okay. Of course, this calcium chloride will be lesser during the dissociation process. So 1 minus alpha, and this one, it will become now the alpha. It splits to separate, okay, species, okay, like that. Okay, so like that. So now our dissociation factor I is equals to the total species after dissociation, like this, and the total species before dissociation. Okay, like this. So we need to cancel out the A here, right? Sorry, this is 1 minus A, sorry. So will be now equal to 1 plus A over 1. One minus A, it's not I. Sorry for that. Okay, and then like this. Perform the basic mathematical operation. A is equals to 1. Degree dissociation equals to 1. Then 1 plus 1 is equals to 2 over 1. So our Vanthoff factor is equals to 2 for the calcium chloride. Okay, like this. It's just the same with the, Vanthoff factor, dissociation factor and Vanthoff factor here. Okay, this is the first form. Dissociation factor or Vanthoff factor is the 1 plus degree of dissociation A times the bracket of the total number of ions V minus 1, and the second formula of the Vanthoff factor and dissociation factor will be this one. I is equal to total number of species, okay, after dissociation at time is equals to T over the total number of species during dissociation. Oh no, before dissociation, sorry, this denominator. Okay, before. So after divided by before dissociation is equals to I. Okay. So that's why we can conclude that Vanthoff factor I is equal to dissociation factor, and it's equal also the total number of ions if we treat our degree of dissociation is 100% or our alpha is equals to 1. Okay, so don't forget this basic concept. This will be used also in equilibria chemical reactions, the solubility product reactions. But what is the difference is only letting X for alpha. Okay, letting X for alpha, let's say 1. So 1 initially for this, let's say chloride or HCl. Okay, and then in the reaction it will split to hydrogen plus chloride. Okay, like that. So during dissociation, okay, it will become 1 minus X for HCl, hydrogen chloride, hydrochloric acid. It's just the same, hydrogen chloride and hydrochloric acid is just the same. Okay, so 1 minus X, and now our products H positive will be X plus X plus X, something like that. Okay, and then our before dissociation at times equals to 0 will be 0, 0 for H positive and chlorine respectively, and we have 1 initially for HCl because HCl alone is 1, okay, because there is a coefficient of 1 because it's not stated the concentration initially. If it is stated, let's say 0.5 molar of HCl like this, okay, dissociates into H positive and chlorine, so it's no longer also 1. It should now be equal to our initial concentration will be equal to 0.5 before dissociation, okay, and during dissociation or after dissociation it will become 0.5, okay, minus X, okay, which is our degree of dissociation. So most textbooks are using X, not the alpha, okay, not the alpha, okay. That's why like this, KSP is equals to X times X over 1 minus X. So X is the degree of dissociation, okay, like that. So KSP, solubility product constant, something like that, okay, if you can remember that one, okay. And then X is merely the concentration, like this, okay, concentration or degree of dissociation or the concentration, something like that, okay. So in my example, there's no specific how many molar or how many number of moles like this initially, okay, no such specific identity of the moles of solute like this, so, or concentration like plus one, so it's up to you to solve the problem like this, okay. Okay, I hope you understand now why Vanthoff factor is equal to the dissociation factor and why it will be equal also to the total number of ions. So this total number of ions determination or dissociation is very also useful in the redox equation, okay, reduction and oxidation reaction, okay, like that. The just the same. If you have the knowledge, you can easily apply the redox reaction in acidic solution, redox reaction in the basic solution, something like that. Okay. That's very useful. Okay. Okay, very clear now. So later I'll be discussing also the equivalent weight, the number of grams equivalent to weight, like this, blah blah blah. Still a colligative property, normality, molarity, okay, freezing point elevation, freezing point depression. Freezing point is always depression, okay. Boiling point elevation is always elevation, boiling point, okay, like that. And the osmotic pressure, okay. So these are all about colligative properties. Okay, my colligative properties discussion lasted for how many days discussion, because we have so many topics, right? Colligative properties, we have the vapor pressure lowering, like this, the freezing point depression, the boiling point elevation, osmotic pressure, and also the molality, normality, okay, including this Vanthoff factor, dissociation factor, the degree of dissociation, like this, okay. Very important also. So meaning to say, in the colligative properties, we are not concerned for the what particular products will be come out, okay, in the dissociation. We are just focusing on the number of ions and molecules only, the number of ions for the Vanthoff factor, dissociation factor, okay. So more on the quantity, okay, quantity, the amount, or how many, the number of particles, like this. We're not after for product like this, what is the nature of this product, like this, blah blah blah, so on. So okay, we're more concerned on the charges, like that, the number of ions, like that, okay, or the number of particles, say ions, like this, okay, ions plus ions equals to molecule, something like that, okay. And ion is referring to could either be a positive or negative charged particles, negatively charged particles, or a positively charged particles, something like that. So polar ions are the negatively charged particles. That is what we call as an anion, okay, something like that. And the other one is the cation, something like that, okay, like that. So if you remember that one, cation and ion. So cation, positively charged particles, and ion, negatively charged particles. And then in electricity, you know, electricity, uh, this this negatively charged particles is the cathode, something like that, reverse, and this positively charged particles will be the anode, something like that. Will go to the anode like this. The negatively charged particles will go to the cathode. The positively charged particles will go to the anode. Like that. Just help me out for that. Maybe I'm wrong. Just review also the electricity of the electron. You know, a diagram like that's electrolysis also. Okay. It can be explained also for the electrochemistry. Okay. This is called actually electrochemistry, dealing with negatively charged particles, positively charged particles, okay, and a chaos solution. So in that manner, this is electrochemistry, meaning to say chemicals will produce electricity. This is electrochemistry, meaning uh, the the chemistry, which are particularly the chemicals or the electrolytes, the sodium, the chlorides, like that, will produce an electricity. That's why it's called electrochemistry. Okay, meaning to say it will produce electricity from chemistry. Okay, electrochemistry. Or we can have the electrochemical reactions to produce electricity. Okay, through these concepts. Okay, negatively charged particles, positively charged particles in a K solution, something. There must always be water, like blah blah so and so. Okay, and then, what do you call it one? Cells, cathodic seed. Okay, so this principle will be applied there also. Okay, so thank you so much for watching this discussion regarding the Vanthoff factor and dissociation factor, why it is equal, and it's also equal to the total number of ions. Okay, okay, and no longer try to substitute them in the dissociation factor formulas. I, two i's, okay, we will immediately detect that to the total number of ions. The formulas of, in the end, then if you will try to use the two formulas of degree of dissociation, but degree of dissociation. That's why our total number of ions, V, in the formula of the dissociation factor I, or the Vanthoff factor I, okay, will be always equal to the total number of ions during dissociation. Okay, like that. So during dissociation, meaning positive charge and the negative charge elements. For example, in calcium chloride, the calcium positive 2 and the chloride negative 1. Okay, like that. And then we balance everything there through charges. Okay, it's not through atoms balancing, but it's through charges. That's why ions. Okay, and we refer to the coefficient. Okay, and the subscript plus the coefficient is and the other element also, something like that. Okay, thank you so much. If you think you learned something for this discussion, then you can like, The notification bell. Meron ba akong notification bell? God bless. Bye-bye.